Welcome PlayBASIC coders. Here's a star tunnel. We have two versions, the simple version, this one here. Let's run it. Beautiful. This works as you expect. We're computing the position of every dot on screen. We're doing a bunch of manhandling through it. There's another way of doing it. This one works in a very peculiar way. We have one program that generates the source code of the demo, and it unrolls or pre-calculates all of the dots. That's our launching program. This is our effect. So we get double the performance by doing a bit of work and building the source code with all of the pre-solved positions for all of the possible dots of the effect. That's pretty much how most demo effects work. They're a combination of either animation sometimes or unrolling the code to such a degree that you're filling up the memory to make the effect sort of feasible on that machine, particularly on classic 8-bit and 16-bit / 32-bit machines. Like for the 8-bit era, you're talking about 64s and Spectrums and Amstrads, those machines, and 16-bit era, you're talking more about the Amiga, Atari ST systems, into the sort of the full 32-bit era of the higher end Amigas, in particular, where memory is unrolling the code is less of a punishment. The way this works is we kind of act out the effect and output the code. So anything that's calculated we can do on this side of the equation. And this is the outputted code here. All the stuff in the string here, this is what it's creating. If we have any variables we want both sides to understand, we have a variable here and I output it as string cross. Our main loop, each ring is just drawn out as Z depth. So we are computing the depth and the radius of the ring at this depth. And we're making one fundamental difference. We're calling a function. We could just have a ghost up here, really. Wouldn't make any difference. To call our ring and return. Let's look at the code it produces. So this is version 2, and it outputs the code into the example file. Now it's created 700K of code. And when you look at it, you'll see why. This is our simple header, which we saw in our program, and every little piece up here is just a list of fast dots. So this is drawing that ring at every possible size that's required for the demo. And towards the end here, the functions get simpler and there's nothing in them actually towards the end. That's how we unroll things on a large scale. Most of this program here is actually, because we're generating the source code for another program from a PlayBASIC program, we have to call the compiler again to run it. So this compiler run stuff over here is doing that sort of magic for us. It's not pretty, it's just doing that work for us. I think the best example of this I ever remember seeing, particularly maybe late 80s it would have been, was in a demo called, I think it's Interference by Sanity. And I'd been messing around with plotting dots on that system and going, oh, well, you can get a few hundred on screen, great. So when you see someone do that same kind of effect, and they've got, say, 10 times the performance that you do, and you're going, how is that possible? Well, when I disassembled that code, I found that they computed every possible combination of the rings into these sort of bit set routines. That was how it was done. There was no loops in the output code. It was just, they worked out where the rings go and plotted them in memory and just called the ring they needed to. You've just been watching that now. Fascinating. Another classic usage is Wolfenstein 3D. The vertical scaling is done that way. So we compute what pixels we're going to read from the texture and where they go in the output. And we just have an unrolled bit of code that draws one strip of the wall fragment. You can draw from different textures and different locations, but all of that's unrolled. So there's no interpolation inside those routines. It's just a read and write. Read, write, read, write. Anyway, thanks for watching. I'll see you next time. Bye.